recording.
Yeah, so you just start, you did it for me, the recording. So I don't see who is the one who is trying to present, but I don't hear anybody.
No. So Unai, we don't hear you.
Unai, yeah, we don't hear. Which is bad for presentation.
So I'm going to present
Okay, that's okay now. We can start. Thank you.
You listen me?
Yep.
Okay.
Great.
So this is about workload evaluation of in distributed simulation of discrete event systems that we have developed with some people, as you see in this list. And mainly this is about simulation, as we have seen in the keynote with Rosa, being one of the main pillars in science between the models in theory and the experiments. But we are more interested in simulation of complex systems that with the big size of the models we can get there very easily. We need quite fast to use distributed simulation to cope with the big size of the models that needs to be simulated. That needs, from one hand, to reduce execution time. So that is the number of processors we get bigger. And mainly with large models, we need mainly more memory, something that strangely in later years has been something that has not been very well treated, as a lot of simulators have been implemented in model system languages that don't give a good memory treatment. Mainly we see a development in cloud system where costs are an important thing. Another thing that we have observed in last in a lot of years in simulation development is that work in simulation investigation research have now been seen quite important in commercial outputs that we have seen in real world, and it could be seen as reasons that this has arrived, that the execution platform and the simulation model give some overwhelming complex situation to deal with that has been quite difficult to manage. On the other hand, there have been the two basic strategies, as optimistic and pessimistic ones applied in the simulations, that it can be seen as something that is clear which one you must use in function of which domain or models you are being running. So it's not something easy to propose. In other hand, if you have fast processor or fast communication, you can guarantee performance gains, because that depends a lot of how the model is built and the interconnection in different parts executed in the distributed simulation and the coordination of the simulation, global simulation that is running into. On the other hand, the relations on development cost of the simulation, the performance gains, and utility of distributed simulation is not well understood nowadays. The models must be developed by domain experts, but distributed simulation code must be developed by parallel distributed computer experts. It's quite complex, and dealing between both is not something easily done. On the other hand, what we propose in this context is modeling and simulation of complex systems with Petri nets to try to tackle the challenge that on one hand we have with building the model and the experts of the domain and use the simulation as a forecasting tool in time-critical decision-making process, as we have seen in Rosa keynote. Fill the gap between the model and the execution code in the distributed platform. And this is something that we have some problems where we see that the modeling is one of the most costly tasks in the simulation, but also the code generation, partitioning, deployment, and load balancing, load collection, the different tasks that we have running distributed simulation. It's not something easy to deal with. Well, we have presented till now in a previous conference, we have shown all the methodology from the modeling, high-level modeling in GECON 18, 19, and 20, mainly from the global approach and the methodology, the hierarchical model with components, and last year with the healthcare presentation. And this year we will focus more on the running of distributed simulation from partition, compilation, deployment, and execution monitoring, and some work or future work in load balancing we are been developing lately. So from one hand, we would like also to show a new way to approach the simulation process, where classical approach has been to obtain distributed processes, call it a logical process, where you have compiled in each part the different parts of the global model we are trying to simulate, but they are closed and black box processes that they run, but you don't know very well how to deal with what's inside and how they evolve during the execution of the simulation itself. So this is something defined as compilation time, and but this approach is locked once the compilation has been done, and you are within that. You have no more information you can use in the execution itself. So we propose a new approach where we divide what is the simulation engine from in one hand and the compiled code of the model in the other hand as separate entities. And both of them, when we put together, we call them the simulation processes, not the logical processes. But what did give us is more flexibility to work included in the execution of the simulation, to try to better manage the flow and the performance of the global execution in the distributed one. So what we can do is when we compile the model in each part with the left code as we have called it now, once we can get running each one of them in the execution runtime, we can move different parts of the models while we are running, looking for improve the performance or other metrics we can find in the simulation. So we have something new, is that during the execution, we can have the event dependency network, because we have still the model inside the execution, simplified model, because there are only the transition, but we have all the graph of the relationship between the model during the execution. And in the other half, we have all the dynamic graph of simulation processes that we can deal dynamically during the execution itself. What we can do additionally in this context is that we can partition the entities however we fit, not only before we execute the simulation, but also during the simulation itself. On the other hand, if we see at the load and performance metrics, we have looked a little bit in this domain, where we have taken some metrics relevant to simulation and that can have a clear impact also in distributed simulation execution, where we can have something like the number of scheduled events we will have during the execution that is model dependent. So we have dependency on efficiency of the simulation engine, the infrastructure, the model dependency, and the hardware dependencies. We have the processing event rate, that is the number of events per real CPU time. This is only CPU dependent. Well, how powerful the CPU you have more events you can process. On the other hand, you can have also the rate with approaches can advance a simulation clock as a function of the amount of real CPU time. This is how the simulation time can evolve as a performance metric. And what we can see in a work shown in Gleiser and Tropper in 95, the effective work we can see at the model and CPU dependent, as we can see that the simulation advance rate, the SAR, is how many simulation seconds you can advance in a second. And the load you have in a CPU is how many seconds each simulation second can last. So yeah, you have how you can advance the execution of the simulation in this context. So surely the slowest simulation process or logical process in simulation impose the advance rate to all of the process. All the other ones are waiting for this one to advance. So it depends of complex situation of which features you have in the simulation, how you have partitioned the model, how is the processing unit efficiency of the simulation engine, which is the latency of communications, some crucial thing that we will see later, and which are the dependency relationships in the neighboring simulation processes. So there has been not a lot of work related with metrics in that relate to model and other factors. We can see here in Andras Varga in 2003 that they have shown that the model and the look ahead you use in the distributed simulation and communication latency are related in each other. and how you can deal with these parameters to improve the performance of the simulation process. So we deal with a conservative strategy or protocol. So we have the look ahead. If it is too small compared to the event density, that is the number of events you can deal with in a simulation second, you have a lot of null message, look ahead message between different computers in the distributed simulator that needs to be sent to advanced simulation time. And that's a problem with the bandwidth you are dealing with in communication, and also with performance you can get in. So for example, you can have a look ahead each simulation second, one look ahead message you send, but even you have to occur 6 events or one event each 6 simulation seconds. You need 6 rounds of new message to advance to the next event. This is very, very slow to do all the work. So how you have the model, how you deal with latency, how you deal with the simulation process have a lot of impact in the result. So a good performance you can have if you have the look ahead latency, that is look ahead message latency, sending to another process, simulation process. It must be a lot greater than the inverse of the event density. You need to advance the simulation time with the look ahead a lot to try to process as much as possible events while the communication or look aheads are producing in the system. So the crucial thing is that the look ahead message, the null message, need to reach to the targets before it have no more events to run. So we need to feed the system each simulation process with events to gain performance in the global simulation process. We can see that if we have the variable tau, the latency in seconds, you need to be lower than the difference between the look ahead and the number of simulation time you advance in real time. That was the variable SAR. We transform a little bit better this equation. You can see that the SAR is also the number of events per real seconds, and between the events per simulation seconds. So you can see that the relationship is between the time, the look ahead, the latency of the look ahead message with the events per simulation seconds between the events per second. So we can have equations that are now a little bit more used in distributed simulation, that is the latency in seconds of communication multiplied by the number of events per second needs to be a lot less than the look ahead and the events per simulation second you can get in the system. That is how many events can process the CPU in the time the communication latency you got. You need to have a lot more events you can process in this time to have the machine all the time fed with events in the system. So in Varga, they introduces the what is called in simulation, distributed simulation, the coupling factor lambda. That is the relationship we have seen now. That is the time of communication of a look ahead message L, multiplied by the number of events per simulation second, divided by the latency of communication tau, and the events per real-time simulation, the CPU time you can get. That is what we have told before, that you need to have a lot of events per simulation second, and you need to have a look ahead that gives you a lot of place in simulation second to be able to process in relation to the power of the CPU in real-time process of events you could have in the system. So the lambda coefficient need to be quite large to be able to have good speedups in the system. So in experiments, they have shown that if you have a lambda that is less than 10, usually it's too small to have the distributed simulation gain the speedups and the performance you could have dividing the work. And that lambdas that are greater than 100 is almost always enough, but not always. It's a good metric, but not the only one. It's a reference that in distributed simulation we can have. The problem is that, as we will see in some experiments we have run, this is not the only thing we can infer. This is, but we can, what we can have with Petri net models in all the process of the distributed simulation is that we can infer easily from the model the look ahead and the event density of a partition. So we can have how good we can have the speed up and the performance of the simulation in this partition in particular. So finally, from there, you can have also what is interested to try to get the best performance and the best speed up is something directly related with the cost you will have. Mainly if you can or you want to run the simulations in cloud environments, what cost is nearly regarded. So we have we need to have a precise cost estimation. In the D'Angelo work paper in 2016 and 17, they showed up a cost relationship with have a relation of the cost of the processors, but you have the modulation cost, the time to cost of model execution, between the fraction of the model that can be parallelized, that is how many partitions you can have running at the same time in different computers. What is the synchronization cost between the different parts of the distributed simulation? What is the local communication cost that you are incurring? What is the remote communication cost? Because the experiment we will show has been run in a hybrid cloud context. So we have some communication in some experiments that are between the public cloud and private cloud we have in our team. And the remote communication between all the components. So you need to infer these parameters from the model and profiling the infrastructure behavior to see how the speeds or which costs you will have in function of which model you will simulate and in which platform you will run the simulation. So in the experimental work, As first, we have run the simulation if in our own infrastructure, as you see in the picture. You have there in different forms and components 48 Raspberry Pi with 8 GB of RAM with an Ubuntu 20.04 and with kernel 5.4 and a normal PC with an Intel i5 model 3.5 GHz processor and 32 GB of RAM, and an Ubuntu and the same Ubuntu operating system, but with a kernel more akin with an MAD 44 CPU. So we have implemented a robust version in this first running with the 152 Rust compiler, and with those we have obtained these results. With all the simulation, we have some results there with a model modeling in PetriNet wavefront execution in different model size, and we have run each one 1 million simulation seconds. So the first model is a 3.3 wavefront model that is 9 components coordinating the execution. It has done 60 million events with a performance of 35, almost a little bit more than 35 million events. Real events per real seconds, real time, and a global execution time of almost 1 second. Model with 9x9 wavefront model. We have 23 events per second execution time and a total time of 8. And the largest model with 50 elements in the wavefront model, we have reduced the performance per second of the number of events because of the coordination, bigger coordination it needs to do in the execution of the model. And we see 4,000 seconds of simulation. So they have been run in the PC, and we have run in the Raspberry Pi to compare also which is the performance we can have with a cluster of Raspberry Pi in relation with what we can get with a classical PC in the. So there
you are running short of time. If you can speed up a bit, Unai, I'm sorry.
Sorry.
So if you could speed up a bit because we are running out of.
Okay. Sorry. Thanks. So we can see what is the relationship between the execution of the centralized and the distributed execution in relation also with the lambda coefficient we have shown before. And we can see a little bit curious thing about why we have thought that the lambda parameter is not enough to give up an idea of the execution we can get there. So in the second case, we can have an execution with 2 computers or 2 branches and 2 computers we can use in the distributed model. And we see that in the distributed execution, it is slower than the centralized execution, 2 seconds to 4 seconds. And the third case, where we have more branches and more machines, computers we can use in the distributed simulation, in spite of we have a lambda parameter that is lower, we can get really and improve the simulation time in the distributed simulation in 10 seconds. That is better from the centralized 17 we can get there. So we can see this is not enough to get there. And finally, to compare a little bit, we had previously built because it was easier to implement because we had some libraries and compilation things related. I have a version, and we can see that with the similar models, the execution time and mainly the performance in events per second is a lot lower than the Rust implementation as it is related here. So the Rust implementation give a very big boost in the execution we can get in the simulation process. So finally, to conclude, we can see that we can show that a distributed simulation needs to go beyond the concept of classical logical process to be able to deal with the benefits we can get to get the model inside the execution of the simulation itself. We have shown that some performance metric and cost estimation need to involve the model, partition, communication, latencies, resource simulation, and different elements and the relationships that are between them. The metric we have got can help, but are not still decisive to take the final decision. Can we manage and arrange the different components in the simulation execution? And the use of Petri net models can narrow a little bit the gap between the high-level models, the generation of the code, and the execution of the distributed simulation itself. The current future work we have is that the compilation is a real bottleneck now, because we still have uses for this paper. The previous have a compilator implementation that have problems with the size of the model we can compile with a certain memory size. It's not very big, and we have finalized it in last month a new compiler in Rust trying to deal better with the efficiency in the RAM. In the RAM memory we have in the computer to be able to compile bigger models in the system to do. This is a work in progress. In the other hand, we have been working in the last months in a mechanism to support load balancing, how we can move some parts of the models of the Petri nets compiled models from one machine to another to try to improve the overall performance of the simulation, distributed simulation. We have seen that the look ahead is crucial to see the speed up, and we have implemented the look ahead in the compilation phase to obtain the code that must be run, and also in the execution time, that for some kinds of Petri net models, it's better in one on the other side and see a little bit the relationship. We have done the simulation in heterogeneous infrastructure. We have used a real hybrid cloud with 48 Raspberry Pis we have shown, and also the Google Cloud we have used. So we have a little information about how this is working now. And we are trying to see the strategies about the dynamic partition to optimize the speed up relationship between the speed up and the cost. Mainly, we go to the public cloud in the very element. So I thank you for your attention.
Yes, thank you, Unai. So we are quite late, so we have time for one or two short questions before. In the meantime, the second speaker can maybe share his screen. his or her screen. I'm sorry.
Sorry.
Do we have? Yeah, Karim, you have a question?
Yes. Thank you, Unai, for your presentation. A very quick and general question. You have very much focused on the conservative approach in distributed simulation, trying to identify the look ahead. Obviously, my question is to do with the second approach, which is the optimistic simulation, say, for example, based on the time warp. And I was wondering whether, again, the second approach compared to the first one, conservative versus optimistic, might actually shed some light on the overhead and anything you have done so far.
There is this last thing you have told. There is the overhead, mainly of optimistic simulation, and we have an hypothesis. Is that as we have the Petri net model, we hypothesize that we can get a very good look ahead, so good that maybe we don't need at all to deal with optimistic approaches that are quite more complex and maybe need a lot more resources and a lot more cost in the system you need to run. So we are trying to see if our hypothesis is good enough, and maybe we could offer something better that have been done till now in the distributed simulation community.
Okay, thank you.
Thank you, Karim. So can the second speaker share his screen?
Yeah.
Yeah, okay. So do we have a very last question, a short one, or can we proceed to the next talk? I think thanks, Unai. So then
thank you.
Thank you.
Thank you.
And so now the second talk is a work in progress talk. So the speaker is from I don't know how late it is in Korea, but it's supposed to be late. So thanks for the presentation on the topic is can VM live migration improve job throughput evidence from a real world cluster trace. So you can proceed. Down Park is a speaker.
Yes.